Now we're going to look at the Pythagorean identities, which are these ones right here. Luckily for you, you don't need to memorize these because they will be on the formula sheet, on quizzes, tests, and on the final exam. But what you do need to know is how to use them to prove other identities. So we're going to go through the first example. And this one, it says we're going to use multiple identities to do this. And as before, we always want to simplify the complex side first to see if we can get it to look like the simple side. So let's write out the left-hand side. So there's multiple things I can do. Remember from before, we like to change the cosecant theta to probably 1 over sine theta. So that's something else we can do. Now let's just do that first. Okay, we have fraction plus something that's not a fraction. Might be nice for us to put it under one common denominator. And if I do that, I'm going to have to times this sign here, top and bottom. So we're going to do that. So I'm just going to do sine theta over sine theta, timesing it by 1, so that I can get the same denominator. Now we have cos squared theta plus sine squared theta all over sine theta. Okay, but what is cos squared theta plus sine theta? You look up here, that's equal to 1. So what I can actually do is replace the entire thing, the numerator with 1, and then we're just left with sine theta on the bottom. Oh wait, but that's also cosecant theta. This is our right-hand side, and now we're done. So in this case, we used the identity from last time, using the cosecant is equal to 1 over sine theta. And then we used a new identity that we just looked at. Cos squared theta plus sine squared theta is 1. This next one here is probably better for us to factor it. So let's look at our left-hand side, which has a higher power, and we're going to factor this one. Think of this as a difference of squares. It's kind of the same thing. If I had x squared minus y squared, for example, with the difference of squares, I'll just have x plus y, x minus y. It's the same sort of thing here with it being to the power of 4. So I would have sine squared theta minus cos squared theta and sine squared theta plus cos squared theta. Okay, right away, sine squared theta plus cos squared theta, that's 1. So I can replace that with 1. And then, you know what, that's my right-hand side. And then I'm done. So those ones aren't too bad. We're going to leave the try it yourself, and we're going to go straight to example 2 on the next page. So we're going to use the left-hand side again for this one. It looks a bit more complex on the right-hand side. And now we have a fraction here. Sometimes it's actually easier to manipulate this with this conjugate. So the conjugate is the opposite sign for your denominator. That's usually the conjugate. So we have cos theta, sine theta, 1 plus sine theta, and the conjugate we're going to multiply it by That's going to be 1 minus sine theta, top and bottom. So that's the conjugate. We just took what was in the denominator, and instead of adding, we're going to subtract them. So I'm going to put this under one common denominator now by multiplying the top and bottom. And if I expanded the bottom, because it's 1 plus sine theta times 1 minus sine theta, that's 1 minus sine squared theta. And that is what I will get if I start simplifying the bottom there. Okay, well, I know that 1 sine squared theta, if you looked at the previous page in our identities, that's the same thing as saying cos squared theta. Okay, and then I can see that I can cancel a little bit out by canceling the first term at the top and then another term of cos at the bottom. So then now I'm left with sine theta times 1 minus sine theta all over cos theta. I'm just going to continue up here. Sine theta over cos theta, that's tangent theta. So I'm going to take this right here and just change it to tan theta. And then I'm still left with 1 minus sine theta at the top. And if I wanted to put tan on the bottom instead, that would become cotangent. Because if you take a look, we are almost there. We just need a cotangent at the bottom. So I can throw the tan theta on the bottom by changing it to cotangent. And then now that is my right hand side and I'm done. Now it's a little bit more complex. There's several steps that we had to do. But whenever you see an identity that you have to prove that's a fraction like that, you probably multiply it by a conjugate and it'll eventually give you the solution. Take a look at the next one. Here we probably want to deal with the right hand side because that looks more complex. And the clue here is to write it under one fraction because right now it's separated to two fractions. So that means I need to multiply one fraction by 1 plus sine theta and the other fraction by 1 minus sine theta. So we'll just write it out so you can see what I'm going to do here. So I'm going to multiply the first one by 1 plus sine theta top and bottom for the common denominator. And the other one's going to be 1 minus sine theta. Okay, so we're going to continue with this. And if I put it under one denominator now, I would have cos theta times 1 plus sine theta at the top, and then plus cos theta times 1 minus sine theta. All of this will be over 1 minus sine theta, 1 plus sine theta. Okay. So now what I could do is expand the bottom to simplify it. If I expanded the bottom, I would get 1 minus sine squared theta. And then at the top, I can factor out a cos theta. And if I did that, I'd be left with 1 plus sine theta plus 1 minus sine theta. And if you collect the like terms at the top, my sine thetas would cancel out because it's sine theta minus sine theta. So that I'm just left with 1 plus 1, which is 2. In other words, I have 2 cos theta. But wait, 1 minus sine squared theta is one of those identities I just learned, and that's the same thing as saying cos squared x, or cos squared theta. And then now I can cancel one of the coses, the one at the top, so I'm just left with 2 over cos theta. And that's the same thing as saying 2 secant theta. And that is my left-hand side. And then we're done. A little tricky for this one. It looks a little long and complex, but just take things one step at a time. So remember, when you see a fraction like that, you want to write it as one fraction instead of 2 fractions, and then simplify it down, and you hopefully end up getting the other side. And then moving on to the last example, example 3. Okay, now we're not going to prove identities now, but we're going to solve for them. So this is our equation we have here, and just by looking at the cos squared x, I can change that to sine x, so all of this is consistently sine x. So cos squared x is 1 minus sine squared x, and it's all minus 3x, or 3 sine x, and that's equal to 0. I'm going to expand that too, so it'll be 2 minus 2 sine squared x, minus 3 sine x. And then if I collect my terms, so they're positive, if I move it to the other side, I would get 2 sine squared x plus 3 sine x minus 2. Okay, so now you want to factor it. And whenever you have a number at the front, you're going to use what I call the square box method. You don't have to use that method if you don't want to. But once I find out what the factor is for this, it looks like 2 sine x minus 1, and then sine x plus 2. So all I did was factor that. And from here, we saw a question like this before. We're going to split it down the middle so that I'm solving sine squared x minus 1 is equal to 0. And then sine x plus 2 equals 0 is the other one. So rearranging this, we get sine x is 1 over 2. And it's positive. So we are in quadrant 1 and 2. If you look at our triangles from before, we get sine x equals 1/2 when x is pi over 6. So that's my reference angle. So then x is pi over 6, and then quadrant 2 would be 5 pi over 6. Now let's check our domain to make sure that both of these are in it. And if I take a look, we actually start after quadrant 1 and all the way to 2 pi. So that means I need to discard this solution. It's not in my domain. X is actually only 5 pi over 6 because of our domain. We restricted it, so we have nothing in quadrant 1. Okay, the other one, sine x is equal to -2. This is actually no solution. Sine cannot be 2, ever. So there's no solution to this one. And then that's it. So that's our only answer here. Now, we went through all the examples in this part of the notes. We'll do the try it yourselves in class together.